said something. All right.
You've been going to school with him for a long time. You should know better than to listen to him. That's probably. That's true. That's true. In this case, that was believable.
All right. So solving separable differential equations. So first of all, what's a differential equation? Equation that has a derivative. What's the solution? Antiderivative is involved. It's the original function, right? So y, if it's y prime, then y equals is the solution. So that's what we're talking about. We're talking about solving differential equations. Now over here on the board, sorry for those people recording, but over on the board I've got a list that we made. You don't have to write this down, but I have a list we made with when we first studied differential equations. We have those that we know how to solve, like y prime equals 3x squared. We just do an antiderivative because it's got just an x in it or a t, whatever. We do the antiderivative, stick on a plus c. That's called the general solution when we find the plus c. If we have an initial condition and we can figure out what the c is, then that's called the particular solution. Okay, so we have the general solution with the plus c in it. Particular solution is when we find the c. So we had those. Then we had the kind we can memorize. Now there were two of them. This was Newton's law of cooling, and this was just general exponential growth. And we looked at those, and we didn't know how we could solve those because they had y's in them. But we just memorized the solution we worked with. And then we had those ones we didn't know how to solve. Okay? Now, when you take a course in differential equations, you learn how to solve them. Like in algebra class, we learn how to, in advanced math, in high school, we learn how to solve linear equations, quadratic equations, exponential equations, trig equations, log equations, cubic equations, right? We've got different methods of solving these equations. Take a class in differential equations, you're going to learn how to solve all the different types of differential equations, okay? And what we're going to learn is one of those types today. They're called separable differential equations, okay? Now, in this list, these two are both separable differential equations. These three on the left are separable differential equations. These two on the right are not. And so we will still not know how to solve these at the end of today. But at the end of today, we will know how to solve these. Okay? All right. So here's how it looks. So let's take this as our first example. This was one that we did memorize earlier. The old y prime equals ky. Let's show that we actually do get that solution right there. So let's go through it. Here's how it works. So we'll start with this. First thing we're going to do is we're going to change the y prime to dy over dx. Now actually I'm going to make it dt because normally in differential equations our input variable is t, not x. Joe, you just like to soak it in. All right. So we got dy over dt equals 3y, right? So we're going to do that. Now, what is it? Why the word separable? Well, it just what it sounds like. We're going to separate the two parts here of these variables. Now, we did it back when we did use substitution with integrals, right? We did that then, and that's what we're going to do again. We're going to multiply. The first step is always this. We're going to multiply that dt over to this side. We're going to have a dy on this side, a dt on that side. And now we're going to want to get the y's on one side and get the t's on the other side. Now, constants like the 3, it can be on either side. It doesn't matter. Usually we leave those over here. Now, it's important to understand that when we separate the x's and y's, we're going to always do it with multiplication and division. We'll never do it with addition and subtraction because we can't have a 2 plus dx. You can't have it. You need something times dx or dt or dy, whatever. So when we look on the board here, this one is separable because we could leave the x squared over here. Remember, keep in mind, this would be dy over dx here. So we can multiply the dx over to here. We could divide the y over to here to be with the dy, and the x's would be on this side. Same thing here. I could multiply the y over here, multiply the dx over to here, so it's with those x's. Here, this is a little trickier. How can I get this y over to there? That is it. We don't want to add. That's the key. We're going to divide the whole thing. We're going to treat that y minus 2 as one thing, and we're going to divide y minus 2 over to there. And you just leave a 1 over on this side, and then your dx would come over here. So this is separable, even though it looks like it might not be. We will divide that whole quantity over there. Now this one looks very similar, but because there's that x there, we couldn't do that. We couldn't divide that over there because then we got x's over on the y side. So this one is not separable. There's no way I can separate these. You might say, well, you could add 2x. Well, we can't add 2x because it just doesn't work. It's got to be with multiplication division. And then, of course, this one, same thing. Okay?
Wait,
so
you can't divide that whole thing over?
this you could, or this. You could divide the whole thing over, but the problem is you'd have an x over there on the y side. There's no way to get the x on the x side and the y on the y side. So some can be separated and some cannot. Right? Now, I'm not going to make you figure out which ones you can. You're not going to have to do that. All the ones we give you will be separable. That's the only type we're going to learn how to do. Okay? So, and I'm going to show you on some of the packets where we've got some of these problems as well. Okay, so I'm going to leave the 3 there. I'm going to multiply the dt over to that side. I'm going to divide the y over here. So I'm going to get dy over y equals 3 dt, like that, right? Now, I don't like division. You guys have heard me say it a million times. I would rather this is written 1 over y dy, and then over here I got 3 dt. So that's how you're going to see me write it, and I think that'll be to your advantage to write it down. Now, when you look at that, and you see the dy, and you see the dt, what is missing? What just seems to be begging to be in there? When you look at the dy and you look at the dt, what's missing? Kind of looks like an S. The integral symbol, isn't it? Isn't that where we usually see like a dy stuck on in the end? Is it legal to do that? Why not? We add to both sides, we divide both sides, we do the derivative of both sides. Why can't we do the integral of both sides? We do the antiderivative, basically, is what that means. That's an indefinite integral. Why can't we do the antiderivative of both sides? Sure we can. So that's what we're going to do. So we separate the variables, and now we do the antiderivative, or the integral of both sides, and that's exactly how we do these problems. So, what do you get on the left side?
Natural.
Careful, natural log, absolute value of y. Now, stop right there a second. Most of the time, the absolute value is not going to matter, but you need to put it in there because, and on our quiz, it's not going to matter. We're keeping it pretty simple. And most of our homework probably not going to matter. But there have been some free response questions in the past in the AP test and so forth where it does come into play, especially with an initial condition. So we do want to have it in there, but most of the time at the end, it's just going to kind of disappear and not really matter. Okay? But let's keep it there for now. Now, also, we usually need a plus c when we do the antiderivative. But if we do a plus c and a plus c here, now they're not the same c necessarily. If we're going to get y by itself, remember, because that's what we're trying to do, right? We're trying to solve this, so we're trying to find what y equals, the original function, right? So if we're going to get y by itself, if we got a plus c here, we're just going to subtract it over from that c, and that just gives you another constant, right? Another c. So what I usually do is I don't put the plus c on the y side, because we're going to move it away from that side anyway. And I'll just do the plus c on the x side. So what's the antiderivative of the t side in this case? What's the antiderivative of 3? 3t, and then plus c. Okay? So, didn't do the plus c on this side because we would just subtract it from that c, and that would give us a different c anyway, so we'll just leave it over there. All right, now all that's left is to get y by itself. So what do we do here to get y by itself? E raised to that would equal y. Here's where I'm gonna go ahead and leave the bars on it just for a minute, but we would end up with this right here, right? And then you look at that, you say, well, that's always positive. E raised to something, anything, is always going to be positive. So we really don't need the bars, so at this point the bars just kind of go away. Okay? So like I said, that's what happens really most of the time on your quiz, on your homework. That's always going to happen, so not a big deal. But just understand that it's there, and so it doesn't need to be. Now, you look at this and you look over here, we say, wait a minute, that's not how we memorize that solution. We thought it was going to be a e to the kt. e to the 3t. Well, think back to your algebra here. What's x cubed times x to the third? You add the powers, right? Don't you do that right there? Can't you do that in reverse? If you have a plus in your power, can't you split it into that? So couldn't we do that here? Couldn't we take this and split it, e to the 3t times e to the c? Now what's e? E's a constant, raised to a constant. That's just a constant. So we can take that and just flip it around out in front. That's just a constant, and we can just put that out in front. Now somewhere along the line for these kind of exponentials, they started using a there. So that's what we always used an a, but really it's a c. And that's why there's a c there that's not a plus c, but it's a times. Well, the reason is it was a plus c, but then it turned into a times because of that rule of exponents right there. So whenever we see that like that, we'll usually do that. Okay? Not a big deal. I could leave it like this if I wanted to. I'd accept that answer right there. That's fine. But yeah, it's a pretty good habit to get into. All right, so sure enough, we just solved it. Now, if we'd have had initial condition, we could plug that in and we could find out what C is and we'd be done. All right, so we just learned out how to do that one. Now let's do Newton's law of cooling. Okay, let's solve that one. Now, this happens to be in your packet. Why don't you go ahead and get one of your packets out. It's 2011, I believe. This is problem number 5 in 2011. Get out 2013 while you're at it. We'll do one that's in that. We'll do one that's in that packet as well. At the beginning of 2010, a landfill contained 1,400 tons of solid waste. The increasing function W models the total amount of solid waste stored at the landfill. Planners estimate that W will satisfy the differential equation this for the next 20 years. W is measured in tons and T is measured in years at the start of 2010. That is Newton's law of cooling. Now it's an increasing function. They said that right there in the thing. And Newton's law of cooling, of course, is a decreasing function. Well, that's just because K is positive in this one and it's negative in Newton's law of cooling. That's the difference, okay? So it's still a Newton's law of cooling kind of situation. Because you see you've got the Y or the W in this case in the parentheses minus some constant, which is the 300 right there. Okay, now, so this is a similar kind of thing. Now, we're going to talk through the different parts. Notice we're going to get down here to C. Find the particular solution W equals WT of the differential equation here with initial condition this. W0 equals 1,400 because that's what they told us at the beginning. It had 1,400 tons. So that's our initial condition. So there it is, solving this differential equation right here. It's a separable differential equation. That's what they want us to do. But before we get to that, let's talk about part A. Because this is an interesting problem, and several years in a row, they've had questions like this on the AP test with differential equations. Okay? So, it says use the tangent line to the graph of W at 0 to approximate the amount of solid waste that the landfill contains at the end of the first 3 months. That is when T is equal to 1/4. Now, I want to give you a little sense of this. This should be an easy problem. It sure sounds hard. You read all this, you're like, oh my God, I don't know what's going on. Tangent line, T equals 1/4. What's happening? What's really going on here is you've got this increasing function. I don't know exactly what it looks like. Let's say it's concave down like this. I don't know. And it says that right here, this is how much? If this is the W function, what's this Y value right here? 1,400, right? W function has 1,400 at time 0. But it says use the tangent line at that point. So here's the tangent line right there. Right? And it says at 1/4, that is 3 months, find the point on that line to approximate the amount of solid waste there. Does that look familiar? Have we done that? Have we talked about how if you have a line on a curve, it's tangent at one point, that right around that vicinity, the points on the line are pretty much the same as the points on the curve? Haven't we talked about that? Right? That's local linearity. So right around the tangent point, the points on the line are pretty much the same as the points on the curve. So if we could find that point on that line, that would be an approximation to how much tons of landfill, of waste is in that landfill. That would be an approximation of that. Okay, so let's find the equation of that line. Well, that's easy to do. All we need is a slope and the point. So do we have the point? Sure. That's easy. And do we have the slope? Wouldn't that be W prime? Isn't that right? Isn't that what this is? Right? Isn't that W prime? So what do we plug into W prime? Do we plug a 0 right there? No. Plug a 0 right there? No. What is 0? 0 is t. 0 is time. So it's probably confusing. I did that on purpose. W prime of 0. But yeah, we plug a 0 in for t, but that's not t. What do we plug there? We plug 1400 there, right? We plug 1400. That's a W. W is how many tons of waste at time 0, which is 1400. So we do a 1400 there. What's 1400 minus 300? That's 1100. This is no calculator, by the way. Well, what's 1100 times 125th? 44, right? 125th times 1100, you'd have 4 for every 100. You have 1100, 4 times 11 is 44. So the slope is 44. So the equation of this line, y equals 44, pick a point, x minus 0 plus 1400, okay? And then what, oh, that shouldn't be an x, it should be a t, right? That should be a t. And then what do we do with that? That's the equation of this line. Let's plug a 1/4 in. That will give us this point that's on that line. So 1/4 times 44 is 11. 11 plus 1400 is 1411 tons. Notice they give you some nice, easy numbers to work with. So 1411 tons is our approximation of what's going on there. Now, I'm not going to do part B, but we're going to talk through it here. Well, I want you to finish it later, but not the biggest thing in the world. If I don't remind you, you probably forget to go back to it. Not a big deal. But here's what would happen. It says find this. Now, what is that right there? Second derivative, right? W double prime, right? Well, we could get that from W prime, right? We just do the derivative of this. Now, when you do the derivative of that, which with respect to t, so you're going to have to tack on a W prime, right? So you have W prime equals something, something, and it'll have a W prime in it. Like implicit differentiation, right? Now, they want you to find second derivative, but here's what they want you to do. They say use that to determine whether your answer in part A is an under or overestimate. Look at my picture. Is my picture, if my picture's right, is it an over or underestimate? It's an overestimate because it's concave down. Well, what tells you concavity? Second derivative. So in this problem, they're telling you, because again, I'm guessing some of you would read this question, you'd look at that second derivative, how in the world does that tell me if it's over or under? To me, the whole key to understanding this problem was the picture I drew at the beginning, right? I drew a picture of an increasing function, and when it was telling me to do tangent lines, I was drawing it just to get a visual in my mind of what I was trying to do here. And it just helps so much. So now I look at this, I say, oh, that's over approximation. Why? Because it's concave down. Oh, but I didn't know it was concave down. I just drew it that way. So we do our second derivative, we plug stuff in, and we see if it's concave down or concave up. Then we'll know if it's an over or underestimate. Okay, on to part C. Let's find the actual solution to this differential equation, and that's the new thing we're learning today. So if we go into here, I've got it written right here, so you can put it into yours where you have space. So let's solve this thing. And you don't have a lot of space, I know there. You can go down the bottom there where you got some extra. But so I went ahead, dw/dt. So what are we going to move where? Let's get the dt over to this side.
Well,
Yeah.
distribute the 125.
See, now that's a great question. You could distribute the 125th. However, I'm going to actually caution not to. Let's see, that would be 12. Here's the only reason I'm going to say not to. You can. It'll work fine. Then you would have to divide this whole quantity, right? Some people forget about that. But you would have to divide that as a quantity, and which is fine. When you go to do the antiderivative, then you're going to have to do some messing around with that 125th, so that'll make an issue, kind of. So if I have a constant outside of this, I usually like to leave the constant alone. Just from experience, I found out that maybe that'll be better. So I'm gonna suggest let's move the dt over, and I would say leave the 125th there as well. And then divide this over here. Now remember I said I don't like division, so I'm going to do it as a fraction. And as we've seen, then we're going to put our integral symbols in there. And, right, once again we have a natural log situation, right? Because it's 1 over w. Even though there's a minus 300 in there, that's just kind of a shift, so that's not an issue. So see what's going on? So we divided this over, multiplied the dt over. Yeah, I could have multiplied the 25 and put it on top here, and I could have pulled that 25 out in front here. That'd be fine. But here's the other thing I'm thinking. Why move more than I need to over here with the w? Because I'm going to try to get w by itself anyway. So I'm going to have to move it all back, right? So that's why I'm usually hesitant to move stuff over there if I don't need to. All right, so what is this here on the left? ln, absolute value of w minus 300. Don't put the plus c there, we'll put it on the other side. What's the antiderivative of this? 1/25th t plus c. Right? Now what do we do with this ln? It becomes e, right? It's w minus 300, and actually at this point we can get rid of that absolute value. So it ends up being that right there. W minus 300 equals e to the 1/25th t plus c. And then that's that split apart thing that we talked about, right? So it's really just a c in front is all it is. W minus 300 equals c e to the 1/25th t. And then add the 300. And interestingly enough, doesn't that look like our Newton's Law cooling solution over here? Remember what that was? It was big T plus AE to the KT. And that's exactly what we end up with. Now we're not done this time because we have an initial condition. All right? So we're going to put our 0 in for T and our 1400 in for W. What's that? E to the 0. That's just 1. So C is 1100. So my final equation is W equals 300 plus 1100 e to the 1/25th t. Right? Now, I think in your packet that's all they asked for. Right? But get your calculator, somebody, a few of you anyway, get your calculators out, and let's take that one step further. Because it is a no calculator one, so this would be hard to do. But now let's compare it to Part A. Part A, we approximated how many tons were in the landfill at 1/4 in 3 months. Plug a 1/4 into that. Right? Because wouldn't that tell you how many tons exactly then? Right? So if you let's put a 1/4 in for that T. And let's see what it gave us. And let's see if it really was an over or underestimate. We had 1411. 1411.05. Now it's only 3 months, so right, it's not going to be off much. Remember, our tangent line is really close to the curve. when you get really close to the tangent point, well, 3 months is really close. 1/4 is really close. So it makes sense we're really close. Now, so it turned out we were an underestimate. So it must have been concave up, right? Must have been concave up. So in part B, your second derivative must have come out positive. So it must have been concave up, so your tangent line was an under approximation. Okay, so anyway, that's, I always think we struggle a little bit on differential equation problems. I think it's one of the tougher things we do throughout the year. And when it gets to the AP test, it seems like those are tricky sometimes. But that's what we're looking at. Okay, that you just got to think of the units, what everything represents, and what you're plugging in and so forth. But this is solving separable differential equations. Okay, we're going to practice one more. Now, we've done 2 in a row that had natural log in them. They kind of had this same look to them with ease and stuff. Here's one that's going to be a little different. Go to 2013 packet. Oh, by the way, while you're doing that, let me scroll up here. I was going to show you the scoring guideline for this problem in 2011. This was worth 5 points. So you got 1 point for separating your variables. You got 1 point for your antiderivatives. So if you missed either one of the antiderivatives, you lost a point. You got 1 point for plugging, for even writing down a plus C, because evidently a lot of people miss that, forget that. Then you got a point just for using your initial condition, not even using it correctly, but if you plugged in your initial condition, you got a point. And then if you went all the rest of the way and solved for W correctly, you got the last point. Notice they said if you did not put a plus C in there, you could only get 2 points. You cannot get any more. Sometimes if you forget one step and then do correct work after that, you can still get the later points. But here they said, hey, if you did not put in the plus C, then, of course, what would you do with an initial condition if you didn't have a plus C, right? I mean, what would you even be looking for? So anyway, that's what they're saying. And if you didn't separate your variables or recognize you had to separate variables, you couldn't get any of the points in that part of the problem. Okay, let's go to 2013 and number 6. Okay, consider this differential equation. Let y equals f of x be the particular solution to this differential equation that passes through 1, 0. So there's your initial condition. Notice the similarity here to the last problem. Difference is this didn't have a kind of a story problem feel. It didn't have units and stuff. Write an equation for the tangent line at 1, 0. Use this line to approximate f of 1.2. So very similar situation to what we were doing earlier. All right, but let's do part B. Find y equals f of x, the particular solution to this differential equation. It's a separation of variables situation. So go ahead, you guys try it, and we'll check how you're doing. All right, I want to make sure you don't go too far down the wrong road here. So here's what I did with splitting. Divide the e to the y over, right? Leave the other x's over there on the right. Move the dx over to the right side. Here's where I wanted to stop you from going down the wrong path. Is this ln? No. So often in these separating variables, you divide something over here. So very often you get 1 over y. It's not always ln. If you get 1 over y squared, that's not ln. That's y to the negative 2. Only if it's 1 over y to the first power, or 1 over w with that shift in it, is it ln. You have to write this as e to the negative y. Right? You have to write that as e to the negative y, and then I didn't do anything with that side yet, before you do your antiderivative.
You have to do that before you do your antiderivative, just like this group, right? And I got negative e to the negative one. Like, I just didn't write that stuff.
Oh, you didn't write it,
Yeah.
but you were thinking it.
Yeah.
Oh, that's okay. Yes. Yeah, you don't have to write every single thing you're thinking on these no calculator ones, and they're checking your work and stuff. No, if you did that, and then you just said, hey, I know that antiderivative. Yeah, absolutely, that's fine. But I'm just saying, to help people, you have to think of it as that, yes, to do it. But would you have to write that set? No. Okay, now go ahead and go from there. Go ahead and go from there. And we're trying to get y by itself, yes. Anybody want to take a shot at the answer? I know not everybody's finished yet, maybe. You agree with that? Isn't there a plus c somewhere?
Yeah,
I always figured plus C.
No plus c? What's that, Allie? No. If you have a multiplication inside the log, then you can separate it. So, Carly, what did you say for the plus c? -1. Okay, so what you guys said, Zach and Ryan, was right up until the plus c. Now, the problem with that is 6 points, I think, for this problem. You only get 3 of them if you forget the plus c, right? Again, same thing, they're not going to let you go all the way down. And let's talk through it. So, okay, so here's what it would look like. So from right here, so like Allie said it earlier, the antiderivative of this, we got to remember to kick out that -1, right? The 1 over -1 actually, but still -1. So we get negative e to the negative y equals, and then this would be x cubed minus 3x squared plus c. We always got to remember the plus c on that right side. Very important on this. Now, get the y by itself. Now, I will mention to you that you could find the C at any time from here on out. You could put the 1, 0 in for your X and Y right now. As a matter of fact, it's often easier to do it now than to do it later when you get Y by itself. Okay? Because sometimes getting Y by itself involves square rooting and doing all this other stuff. So like right now on my bottom, on the left side here, if I would have put a 0 in for Y, this would give me e to the 0, which is 1. If I'd have put my 1 in for X, I'd get -1 plus 3, which is 2. 2 plus C equals 1. Subtract 2, I get -1. I found C is -1 real easily right there already. So I could have done that, but I didn't. I went ahead and did this, so I have e to the -y. So now I do the ln of both sides, right? That's how you get rid of that e. Do the natural log of both sides. And you'd have -y equals ln of all of that. The plus c has to be inside the parentheses. That's why you have to do the plus c here. You can't just wait till the very end and stick on a plus c. Right? You can't wait to the very end, get y equals, and stick on a plus c. Just like the ones we saw earlier, the plus c was up in the power. Here, the plus c ends up being inside the natural log. So you have to do it right here when you do your antiderivative. All right, so then we get this, and I divide, put my -1 over to the other side, put that there. Now you can take a negative on the outside, put it inside, make all of that to the -1, but that would just make it more difficult, so I don't know why you do that. Now I went ahead and put in my initial condition. So I put my 1 in for x, my 0 in for y. I ended up with this, but then I had to solve it, so then I had more work than if I had just done it back here. So keep that in mind. Sometimes when you do the antiderivative of both sides, put your initial condition in then before you solve for y. Sometimes it's easier to find the c. All right, so here I had to divide by negative, which didn't matter. Then I get e to the 0, which is 1, equals 2 plus c. So I get c equals -1, and I put it in there. Okay? All right, so in 2000, so that was a little, that was a fair amount harder with all the stuff. So back in 2013, here's what it looked like. They gave 6 points this time. This time they gave 2 points for the antiderivatives, 1 for each. So if you split them, you got a point. If you did this antiderivative right, you got a point, because I think they felt like a lot of people were going to miss this one. A lot of people were going to do ln or something weird like that. But a lot of people would get this right, so they wanted to give them some credit. So they gave 1 point for each on the antiderivatives. Then the plus c was 1 point, the initial condition, and then solving for y was how they graded it. Okay? All right. So that is separable differential equations. Your homework is on the sheet here. There's 7-4. It says you've got, I think, 5 or 6 problems, 17 through 22. Those they're just separable, and you can just do exactly what we've been doing here. They have an initial condition with them, so you're going to find the C value. And then I think 27 and 30 are general solutions. There's no initial condition. So you just separate them, solve the y. Now there is one, I think it's number 20. Sometimes it's just impossible to get y by itself. Sometimes you do your antiderivative of both sides and it's y cubed minus y squared and you just can't get y by itself. Then just stop at that line. So it'd be kind of like the one we were just doing, and if you stopped maybe right here, right there at that line and just left it. Okay, I think that happens to you on number 20. The others, I think you can all get y by itself. Okay, so 17 through 22, 27 and 30, the answer book's up here. Tomorrow, you have Mrs. Kinsley will be here, Mr. Shield will be here on Friday. I'll leave the answer book for the packet for your LH if you're catching up on any of the volume stuff. And then I'll leave this book so you can check today's homework, but you might get a lot of it done in class. Okay?